This is the last class for Chapter 8. In Chapter 8, we studied Hamiltonian mechanics. In the previous chapter, we considered Lagrangian mechanics. From Lagrangian mechanics, we studied how to obtain the conjugate momentum, that is, the partial derivative of the Lagrangian with respect to the coordinate, time derivative of the coordinate. And we have found that the Hamilton's equation of motion is equivalent to Lagrange equation of motion. Euler-Lagrange equation of motion is the second order differential equation, and Hamilton's equation is coupled first order differential equations. And combining the two Hamilton's equations of motion, we were successful to reproduce the Euler-Lagrange equations of motion, the equation of motion that is equivalent to the F equals ma. Today we study Poisson brackets, and the Poisson bracket is to be extended in quantum mechanics to the commutator of quantum mechanical operators. And then we study electromagnetic Lagrangian, and from which we will derive the Hamiltonian for a charged particle, massive charged particle under electromagnetic field. And in addition, the theory will be extended to consider from the theory of the non-relativistic charged particle, we will extend this theory to the case of relativistically moving massive charged particle under electromagnetic field. First, we consider the Poisson brackets. Poisson bracket is defined for two mechanical variables, two mechanical functions. Mechanical function means they are arbitrary functions of canonical momentum P conjugate to the generalized coordinate Qi. And it is a kind of determinant. You will find the first row is the derivatives of f's, the second row is the derivatives of g's. And the first column is the partial derivative with respect to Qi, and the right column is the partial derivative with respect to Pi. Therefore, this determinant is this cross one, so f times fg in the numerator and fg in the numerator. And the denominator is the derivatives qp pq, right? So fg qp pq partial derivative, and then subtract, right? And if there are mechanical n coordinates, then the n coordinates are summed over, so there is a summation, implicit summation over the repeated indices I is assumed. First, the total time derivative of a mechanical function is expressed in terms of the Poisson bracket plus a partial time derivative of that function. Let us check this calculation. First, total derivative of f is a mechanical variable, thus f is a function of momentum and coordinate. So because f is a function of momentum and coordinate, partial derivative of f with respect to momentum and coordinate multiplied by the momentum's time derivative by chain rule and the coordinates time derivative by chain rule, and added up with the partial time derivative. we can apply the Hamilton's equation of motion. Hamilton's equation of motion is given in here. Hamilton's equation of motion is q dot coordinate time derivative is the Hamiltonian's partial derivative with respect to the momentum, and momentum's total time derivative is a minus Hamiltonian's coordinate derivative with negative sign on it. Thus, if I consider this, we have f's p derivative, and p dot is a minus Hamiltonian's q derivative, and we have q derivative of f, and then q dot is Hamiltonian's momentum derivative. All right, and the partial time derivative of f is given here. So we used FG QP minus QP minus PQ. QP appears here. Move this one in here. Q derivative first and H derivative next. P derivative next. So FH and QP. And this one, F first, P, HQ minus, right? So FH, QP minus PQ plus partial time derivative with respect to F. All right. So this one is the Poisson bracket for the mechanical variables F and Hamiltonian. So this is a Poisson bracket for F and Hamiltonian and partial time derivative. So this one is the same as this. So if we make use of Poisson bracket and Hamilton's equations of motion, then we can express the total time derivative of a mechanical function in this way. All right. First, let us recall the determinant property. Determinant composed of two rows. Consider the determinant of the 2 by 2 matrix. And in n by n square matrix, if it is composed of the row vectors, and these row vectors are exchanged, any two row vectors are exchanged, then you have negative sign on it because of the permutation. And then, because of that, we have negative sign if we exchange these two objects, right? And then the total time derivative of a mechanical variable is expressed in this way, but if we extend this one to the quantum mechanical theory, then we will find that this kind of relation exists. If we consider if we do not consider the case of a pure time, explicit time dependence of the mechanical variable, then it is just total time derivative is just a Poisson bracket of f and h. You remember in quantum mechanical operator is usually in the Schrödinger picture, the operator does not have time dependence, and the wave function has the time dependence. But that is called the Schrödinger picture. However, we can absorb that time dependence of the wave function by time evolution operator, and that can be absorbed into the operator. If we define the time dependence, if I move this time dependence and absorb into the operator, we call this kind of way of describing the quantum mechanical system is called the Heisenberg picture. Heisenberg picture has indeed the time dependence. Sure, the Heisenberg picture operator at t equals 0 is equivalent to the Schrödinger picture operator. And if I take the total time derivative of this Hamiltonian operator, we find that the exponential gives I over h bar in here. And h as, and if I take the time derivative of the right side, and we have negative sign, alright, and then this one can be written in the form, for example, h this one is because they are composed of h only, and this one is again therefore this one is h ah minus ah h. That is the commutator. Sure, there is a vector. This commutator is has the sign flip if we exchange the order. Therefore, I have AH commutator Hamiltonian. So Hamiltonian, because U of t time evolution operator, we know the Hamiltonian is the generator of the time evolution. The commutator of an operator with the Hamiltonian gives the time evolution of the operator. Okay, so that is exactly equivalent to the quantum mechanical Poisson bracket, except that we have multiplied IH bar. Okay. Alright, this analysis is given in detail for Schrödinger picture method and Heisenberg picture method to reproduce the result that we just have obtained. Pass. Poisson bracket has various properties. This is because this is a determinant. If we exchange two rows, we have negative sign. So if the argument argument functions are exchanged, negative sign appears. If they are the same, if I put the same thing, so FF Poisson bracket, I just copy this one, minus FF. Move this one to the left hand side, 2 times FF Poisson bracket equals 0. So the Poisson bracket of the same mechanical variable, mechanical function becomes 0. Okay? The next one, if an argument is replaced with the sum of 2 arguments, then it is written in this form, the real part with the same relation. So that's coming from the property of the determinant. If I put the sum of 2 row vectors, the final result is the determinant, sum of the 2 determinants with this AA and CC. Alright, therefore from this we have linear properties of the Poisson bracket operator. These are the proof, detailed proof of those relations. Now we have Jacobi identity, equivalent identity appears in the quantum mechanical commutator. You can check it, but its calculation is too much tedious. But let me pass. So what about the Poisson bracket of 2 mechanical variables, especially for the generalized coordinate and canonical momentum? You remember in quantum mechanics, the commutator of coordinate and conjugate momentum is always IH bar delta AB. Momentum, it is always vanishing, and coordinate, always vanishing. Okay, remember this. So let us check what happens. Just like what we have considered for the time dependence, the total time derivative of mechanical function, we find that if I rewrite the Poisson bracket in the case of the quantum mechanical analogy of the Poisson bracket is the commutator, except that its value is multiplied by IH bar. Alright. So let us check if it is true. Poisson bracket QP, coordinate and conjugate momentum. First, Poisson bracket QP. So QP. Derivative should be made with respect to QP, PQ, and put the negative sign on it. Partial derivative is coordinate, so chronicle delta IA. Momentum. Therefore, the coordinate, momentum, delta IB. Coordinate momentum vanishes, momentum coordinate vanishes. Therefore, we have, if I sum I up, we have delta IB. So the result is, for example, in a single particle 3-dimensional case, it is Q1, P1 equals 1, Q2, P2 equals 1, Q3, P3 equals 1. And Q1, P2, if the indices are different, 0. Q1, Q3, 0. And so on. So that is the chronicle delta AB. We remember XP equals IH bar. But XI PJ equals IH bar delta AB in quantum mechanical case. Next one, Poisson bracket of coordinate. QQ, 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 QA, QB, QA, QB, QA, QB. The derivative will be made QP minus PQ. That is the Poisson bracket. So coordinate Kronecker delta, but coordinate momentum vanishes, coordinate momentum vanishes, coordinate delta. However, all of the non-vanishing vector is multiplied with 0, so this is completely vanishing. Momentum. The PA, PB, derivative will be made QP minus PQ. Alright? Therefore, what you find is this is always 0. Quantum mechanical counterpart also vanishes. It survives only in the case of coordinate and conjugate momentum. Let's check quantum mechanical commutator QAPB, because QAPB minus PBQA, right? The PI will be replaced with h bar over I, and the coordinates derivative, right? Q doesn't have to be x. Q may be theta, or Q may be phi, something like that. So if it is the case, the conjugate momentum is linear momentum. If it is the case, the conjugate momentum will be the angular momentum. Alright, so we have two operators and two operator flipped. This derivative applies to the coordinate or outside. So if I take the derivative here, I don't have a derivative anymore. If I do not take the derivative here, then it will pass. If it passes QA, then in this form. So these two cancels, and the quantum mechanical commutator is IH bar delta AB. This reproduces the result in here. So next we consider Liouville theorem. Liouville theorem is very important for phasor space. It is important for classical mechanics and important for the quantum mechanics and quantum field theory too. The phase space is constructed on the two dimensions. If I have n coordinates, we have n coordinates and n conjugate momentum. Phase space is something like that. If I have P, Q, and P harmonic oscillator, the kinetic energy is 1/2 of kq squared plus p squared over 2m, something like that. This energy, this is a Hamiltonian. This Hamiltonian is fixed. Then phase space, this particle runs the path on this phase space. This is the case of one-dimensional case. So phase space is generated by P and Q allowed values. In case we have n coordinates, n momenta, then we have this is a two-dimensional phase space. One-dimensional particle motion is described in terms of two-dimensional phase space. If I have n degrees of freedom for the coordinates, then our phase space is nqi's, npi's generates Euclidean space that is composed of two n variables. So we need to consider the 2n-dimensional Euclidean space that is generated by this n coordinates and n conjugate momentum. So 2n coordinates. Thus, we have canonical coordinate and it's a conjugate momentum, and phase space is generated by n coordinates and momenta. Let us define the tau, that is the mechanical system's phase space element. Phase space element means Q runs from Q1 runs from Q1 plus dQ1, Q2 until Qn runs from Qn to Qn plus the dQn, and momentum also. So this volume, and rho is multiplied to define the number of states, number of possible mechanical states. So this is the probability density of finding the state within the region. Okay? Let us first consider the case that the rho is a mechanical variable of two n variables, n coordinates and n momentum. A mechanical variable's total time derivative must be expressed in terms of the sum of the partial time derivative, and by chain rule, because rho is a function, is a mechanical variable, it must be a function of the coordinates for the phase space. Coordinates for the phase space means qi, all the qi's, all the pi's. Alright, if I consider both of them and multiply the time derivative of this coordinate, time derivative of this momentum, what you obtain is the total time derivative. Once qi dot and pi dot is obtained, we can apply the Hamilton's equations. Qi dot is a Hamiltonian's partial derivative with respect to momentum, and pi dot is a minus Hamiltonian's coordinate partial derivative. If I substitute this one in here and here, what we find is rho h and pq minus I. Aha, this is the Poisson bracket of rho and h. The total time derivative of the probability density function is partial time derivative plus Poisson bracket of rho and Hamiltonian. And then, alright, we define, if we consider the partial time derivative of probability density, we might want to consider the conserved quantity. If, for example, probability is conserved, just like the mass is conserved and the charge is conserved, we can define the current density. Current density should be a function of, should be rho times velocity. In here, we are considering the coordinates of the 2n-dimensional phase space are coordinates of 2n-dimensional phase space are p1 to pn and q1 to qn. There are 2n coordinates in Euclidean space. So the velocity in this Euclidean space is just the time derivative of each coordinate, right? This is the time derivative of velocity in this phase space, Euclidean phase space. That. So density multiplied the velocity should be current, and in that case, then this probability density must be conserved. And in here, this divergence J is a 2n dimensional quantity, right? And just like that, the derivative, this gradient is again 2n dimensional objects. This is derivative of a first. This is a derivative of a first Euclidean one. This is the derivative of the second Euclidean coordinate, and so on. 2n, right? But this is nth. P1 derivative, Pn derivative, and Q1 derivative, Qn derivative, and so on. If I consider the fact, the divergence of current density, this current density is rho times velocity, and for I equals for the first n components, and this is the last n components. J is in here, first n components, rho pi dot. The pi derivative. The last n components, rho qi dot, qi derivative. If I consider this, I have two pieces. Rho is factored out. This derivative is applied to the last factor. These two, pi derivative for the pi dot and qi derivative for the qi dot in here. And first one is rho derivatives with respect to pi, rho derivative to with respect to qi, and pi dot and qi dot is factored out. We remember that this one is just this total time derivative of rho is a partial time derivative of rho plus pi round rho pi dot and qi around rho qi dot, right? This one. So this one is the same as this. So this one, right? Therefore, we have this contribution. This one, we can make use of the Hamilton's equation, pi dot, qi dot. Qi dot is Hamiltonian's partial derivative with respect to pi. So this one is replaced here. So qi derivative and this Hamiltonian's pi derivative. Okay, and next one, this one is moved here, pi derivative, and this is Hamiltonian's qi derivative. You can see these two are the same, and derivatives are commutative. So derivatives are commutative, they cancel. Eventually, this guy is equal to total time derivative of rho. But we have constructed that this one is a conserved quantity, so this is 0. That means the total time derivative of the density is 0. This is a constant of motion. That means a phase conservation. Okay. Detailed calculation can be repeated in here. Alright, let us consider as a last step, we consider charged particle motion in the electromagnetic field. The charged particle massive charged particle's motion in the electromagnetic field. And first we will consider the non-relativistic case, and we will extend that method for the relativistic case. And at the end of the day, the equation of motion will be derived. You will find that in both non-relativistic and relativistic cases, the equation of motion is exactly the same as the Lorentz force. That is, charge Q under electromagnetic field E and B is Q E plus Q V cross B, something like that. All right. First, let us consider Maxwell's equations. Alright. First, the Maxwell's equations. The Coulomb's law of force is formulated in a compact way in integral form, which is called the Gauss law. Gauss law is this left-hand side is phi of E. The electric field flux integrated over a closed surface which encloses the volume V. E is equal to charge enclosed inside the volume of V divided by the electric permittivity constant in the SI unit system. But however, in this class, let me make use of Heaviside Lorentz unit. In Heaviside Lorentz unit, the E field dimension and B field dimensions are the same. In that, and epsilon 0, mu 0 does not appear. So the expression is very compact in this frame. Okay, let's see. The electric field flux is proportional to the charge enclosed inside the volume, whose boundary is this closed surface. And we can make use of the divergence theorem. If I apply the divergence theorem, this the surface integral can be expressed in terms of volume integral of the divergence of the this integral. This is electric field, right? So if I make use of divergence theorem, this becomes volume integral. And the charge enclosed inside the volume should also be expressed in terms of charge density integrated over that volume, right? Charge density integrated over that volume is like that. But here you find this integral over the same region. Let me just shrink this volume into a very tiny region at x. If it is a very tiny region, then we can say these two integrand must be exactly the same. Okay? Therefore, divergence E equals charge density divided by permittivity constant epsilon 0 in the SI unit, and in the Heaviside Lorentz unit, divergence E becomes a charge density rho. We know that the magnetic field is generated by magnetic dipoles, N pole, north pole, and south pole. And nobody can separate the north and south pole at all. And always a dipole structure. And non-existence of the magnetic monopole states that the magnetic charge is always 0. So because the magnetic charge is 0, we can apply the same divergence theorem with E electric field replaced with magnetic field, and the right hand side, the charge density, the magnetic charge density must be 0. So if I substitute 0 in here, the resultant Maxwell's equation for the Gauss law for the magnetic field is divergence B equals 0. The third Maxwell's equation is Ampere's law, and actually Maxwell-Ampere's law. Ampere's law is related to the real current, and Maxwell-Ampere's law includes the displacement current. If I have a current in space, the magnetic field is generated by the Ampere's law. There's a mu 0 I on the right hand side, and here this I can be expressed in terms of current density multiplied by the scalar product of area on the surface S, and that surface boundary is the closed path. So this is a surface and this is closed path, and the closed path is the boundary of that surface. Alright, therefore we find that this magnetic field, the line integral along a closed curve, is a mu 0 times I, and I is expressed in terms of the current density scalar product with the cross-sectional area. Alright. In addition, magnetic field can also be generated by the changing electric field. That can be obtained by considering the parallel plate capacitor, and the current I is flowing, and in here this is just a vacuum. However, even though there is no current at all, we have magnetic field. The same structure of a magnetic field appears in this vacuum, although there is no current at all. This is called the displacement current. In here, ID, displacement current is obtained due to the existence of the electric field's time derivative. If the electric field changes with time, magnetic field is generated. Therefore, we call this one to be the displacement current. All right? Alright, so now let us make use of the Stokes theorem. Stokes theorem states that the line integral over a closed path of B is expressed as the curve's scalar product with the areal element that is enclosed by the closed path. Okay, so right inside, the currents are expressed in terms of the area surface integral with the scalar product of the sigma of this amount. Finally, in the SI unit, curl B is mu 0, G plus epsilon 0, round E or round T. And in the Heaviside Lorentz unit, curl B is 1 over C multiplied the current density plus round E over round T. Alright. Finally, we need to consider Faraday's law. Faraday's law is the one for example, if we conservative force expressed in terms of position only, then the potential energy as well as the potential energy, the electrostatic potential must not change if we return to the same point. However, if the time-dependent magnetic field appears inside the region, because of the Faraday's law, we have non-vanishing potential difference, right? That is a Faraday's law. And the right side is the minus time derivative of the magnetic field flux passing through the surface. That surface is enclosed by this closed path C. Therefore, if I apply the Stokes theorem once again for the Faraday's law, what we obtain is the curl of the electric field is a minus round B over round T for SI unit, and is a minus 1 over C magnetic field's time derivative for Heaviside Lorentz unit. Next, we consider how we can express the magnetic field and electric field in terms of potential. And those potentials are actually the scalar potential and vector potential. Because you must be familiar with the relativistic theory, those potential will compose the full vector potential, that is whose time component is the scalar potential and whose spatial component is the vector potential. First of all, let us consider the fact that there is no magnetic monopole. If there is there is no magnetic monopole, divergence B equals 0. Thus, we can always find a vector field A such that magnetic field is expressed in terms of curl of A. It is because if I put curl A to here, divergence curl A. This is a triple scalar product style. So epsilon ijk is multiplied, and then these two derivatives are commutative. Therefore, symmetric multiplied by anti-symmetric vectors, resulting in the vanishing component. So in any case, curl A must express the magnetic field. There exists a curl A such that the magnetic field is expressed. Next, we consider the Faraday's law in the derivative form. The partial differential equation for the Faraday's law is a curl E minus 1 over C, magnetic field's time derivative. So we find that this one, in here we have magnetic field B appears in here. If I substitute this curl A for the magnetic field, we find this one. As we know, the two derivatives are commutative, so I can pull out this curl and insert this partial time derivative inside and move this right side to the left hand side to find that curl, open the parentheses, E plus 1 over C, vector potential time derivative, partial time derivative multiplied by 1 over C. Therefore, E is equals 0. But we know that any curl function equals 0. Alright, so if I consider this one to be minus gradient phi, which is a scalar function, this scalar function will give if I insert the curl of gradient, this one always vanish. We have checked it explicitly in the vector calculus chapters, so it is exactly 0. So I can always find the scalar field phi that satisfies this relation. If I move this one, the vector field time derivative to the right side, the electric field expressed in terms of minus gradient phi minus 1 over c and the partial time derivative of vector potential. And coming from this magnetic field is expressed in terms of the curl of the vector potential. As I already stated that these two potentials, the scalar potential and vector potentials, are components of the full vector potential, right? Next, we consider the gauge transformation. Gauge transformation is a transformation of the gauge fields, this phi and a, scalar potential and vector potential, but that keeps the electromagnetic field the same. So the physical fields, electromagnetic fields are invariant under gauge transformation. This is the form. Phi is transformed into another scalar field, phi prime, which is phi plus 1 over c, partial time derivative of arbitrary time-dependent scalar field chi. And the vector potential A is shifted from A to A prime, and that A prime is vector potential subtracted by minus gradient of this scalar field chi. Let us check if it is true. E prime, let us suppose that this may be different from this because we are substituting different functions in here. So minus gradient phi prime in here, minus 1 over c time derivative of partial time derivative of a prime. If I substitute in here, then we have minus gradient phi, and minus 1 over c time derivative of gradient chi. And then we have this term, this contribution is a minus 1 over c a, it's time derivative. And substitute in here, it becomes 1 over c minus plus time derivative of chi gradient. But we notice that this is positive sign and this is negative sign. They cancel exactly. So it becomes E prime becomes minus gradient phi. Oh, this form is exactly the same as the original one before transformation. Therefore, this contribution, if I introduce these two contributions in here, electric field does not change at all. In addition, we need to check what happens to the magnetic field. If I substitute A prime in here, A prime in here, I substitute A and minus gradient chi. Minus gradient chi's curl. It must vanish always. Therefore, it is a curl A and the same as the original value. Thus, the phi prime and A prime also give the same electric or magnetic field. Therefore, just like the potential in the classical mechanics for normal particles, and the shift of the potential energy does not change the force at all. However, in the electromagnetic case, it is quite complicated. Even though we have some freedom to choose the potentials for phi and A, but choice of phi and A are correlated, and we must not vary a single one arbitrarily, but they must have some correlation. This shift is actually, if we consider this into relativistic approach, this is just shift of this 4 vector potential by 4 vector derivative, covariant derivative of chi. Covariant derivative of chi this covariant derivative of chi is just so we have 4 vector potential A, and A mu goes to A mu prime is the gauge transformation, that is A mu plus round mu chi, and that is phi A plus this one. Therefore, this is exactly what we have written in here. And actually the E field and B fields are non-vanishing 6 components of the field strength tensor. And this one is expressed in terms of electric field and magnetic field only. And if I make use of that fact that under gauge transformation A mu goes to A mu plus covariant derivative of chi, then if we substitute f prime mu nu equals around mu A nu plus around nu chi plus minus around nu A mu plus around mu chi, and you will find mu A nu minus mu A mu plus round mu minus round mu chi. You know the derivatives are commutative. There is this vanishing. This is exactly the same as the electric field and magnetic field. So this one is, they are exactly the same. Alright, so next step, we consider this. Wait a second, I need some water. Okay. Let us consider the electromagnetic charged particle motion under electromagnetic field. If we consider the relativistic theory, it is very easy to find that even though the charged particle is not moving relativistically, the electromagnetic field is already relativistic. The photon is the communicator of the electromagnetic field, and that always flies with the speed of light. The potential energy, electrostatic energy, only contributes to a charged particle interaction when the charged particle is not moving at all. And once you make a boost, Lorentz boost from the rest frame of charged particle, this potential energy, this is at rest, and this one can be expressed in terms of a covariant Lorentz invariant contribution. And we will find that this generates the additional piece that is V dot A style. And right now we want to consider this expression, whether it is really consistent with the Lorentz force or not. All right. First, let me make use of this Lagrangian, and to find out the conjugate momentum pi, what I have to do is take the partial derivative with respect to the time derivative of the coordinate. And this is the kinetic energy and electrostatic energy, and this is related to the interaction with the particle with the vector potential. If I take the derivative, then this one is xk dot squared, and this is potential, electrostatic potential phi that does not depend on the velocity of the particle. The potential energy depends only on position and time, something like that. Therefore, this one vanishes. If I take the derivative of this one, again, vector potential is independent of velocity of the particle. Therefore, we just take the derivative of this vector. If I do that by making use of chain rule, mxk dot appears and derivatives of the velocities. So this one gives the chronicle delta ik. If I take the derivative of this, and that is to take the derivative of this vector, and another chronicle delta ik appears. This is just what I have stated. The electromagnetic potential does not depend at all on the velocity of the particle, but it just depends only on the position and time. Alright, so if I sum over k, what I obtain is the conjugate momentum, this canonical momentum along the conjugate, along corresponding to the coordinate xi is obtained by mxi dot plus q over c vector potential. In a vector form, we can write that. So even I can write in this form, mx dot equals p minus q over ca. I have moved this vector potential dependent term to the left hand side. This is the only difference in the presence of the electromagnetic field is this one. We had for the free particle, if there is no electromagnetic interaction, especially if there is no magnetic field, the mx dot was just the momentum. However, mx dot is not a momentum at all, and it is a momentum subtracted by the q over c vector potential. That is quite important. Let us continue to find out the corresponding Hamiltonian. Hamiltonian can be found by taking the scalar product of the canonical momentum with the velocity subtracted by the Lagrangian, right? You know, p dot x dot, and what is that? 1/2 mv squared. I can put m inside, so 1 over mx dot squared, 1 over 2m mx dot squared. This is the kinetic energy, and then this is this, and then minus q phi. This is the Lagrangian, so subtract the Lagrangian. Minus q phi becomes plus q phi, and this contribution appears with negative sign in here. Now let us combine these two pieces. Both of them has the vector of x dot. The x dot vector is vectored out, so factorized form is p minus q over ca dot x dot, right? And this original kinetic energy piece is copied in here, and electrostatic potential turn moves here. Now let us make use of this one. Mx dot is replaced with momentum p minus q over ca. Mx dot is moved in here. So mx dot. So this is 1 over m p minus q over cm a. And this one is 1 over 2m mx dot p minus q over c a squared and q phi. And these two are the same except for the factor. They cancel partially. We end up with Hamiltonian, which is 1 over 2m p minus q over ca squared plus q phi. Now the replacement can be found from the free particle. Free Hamiltonian was this one, but h goes to h minus q phi, this electrostatic energy. Momentum p is to be replaced by p minus this one. And actually the Hamiltonian is the scale of energy, and PC has the scale of energy. So if I use that, PC goes to PC minus QA. Or you have noticed that this is a kind of 4-vector. Energy divided by speed of light and momentum is to be replaced with this one. This is just like a 4-vector momentum plus a minus phi a. Aha! So this is p mu and this is a mu. Aha! In the presence of the electromagnetic field, there is a replacement. Simple form. This compact form explains everything in here. Okay. Now we have the charged particle Hamiltonian moving inside the electromagnetic field is expressed in this form. And in quantum mechanics, what we want to do is just to replace the momentum with an operator with a derivative. In case we are working on the configuration space. In the configuration space, the momentum appears as derivative. But if we are working on the particle physics, then we might want to work in the momentum space, in which the coordinate is expressed as the momentum's derivative instead. Anyway, if you are considering the bound state problem, then configuration space is much better. In the configuration space, the momentum operator is replaced with the derivative, and that can be inserted in here. You will find the Hamiltonian and quantum mechanical system has this form, and this one gives the dipole structure. Dipole approximation is coming from this Hamiltonian. Next, we consider the equation of motion, that is the Hamilton's equation motion. We remember the coordinates time derivative is Hamiltonian's momentum derivative, and coordinate momentum's time derivative is minus Hamiltonian's coordinate derivative. So this is the explanation, and this is the derivation for that Hamilton's equations of motion. If I take the derivative with respect to the momentum, I just copy this Hamiltonian for a charged particle in here to find that the usual calculation, find that xi dot is 1 over m pk over q over c ak. Therefore, this is equivalent to what we have obtained with the Lagrangian. We have obtained the conjugate momentum, and that is the first equation. First Hamilton's equation is just definition of the definition of the conjugate momentum p. The second equation is, of course, this one is a minus momentum's time derivative. It is the Hamiltonian's spatial derivative gradient. Hamiltonian's spatial derivative involves the derivative of momentum. We do not have to consider derivative of vector potential and derivative of the scalar potential. If we keep track on this calculation, we will find that this is a kind of form. This is the by definition, pi is if I copy this one in here, if I have substitute in here, then you will find the double time derivative of coordinate plus total time derivative of a vector field. And if I combine these two pieces, what you find is this one. Here, minus sign is multiplied to find the minus g gradient phi, and this contribution gives this negative sign ai q over c, and where is it? Here, total time derivative of A expressed in terms of this. What I mean is total time derivative is a derivative of a partial time derivative and derivative with respect to x, and then multiply with wait a second. So this one in here we have replaced the k dependence index k with jj here, right? So finally we have this relation. Thus, we can make use of the definition of the the potential expression for the electric field and potential expression for the magnetic field. If you follow the calculation, at the end of the day, you will find this kind of form, and there's the electric field appears. Electric field QE is the electrostatic force, and Q V cross B style. That is the magnetic force. And actually this Lorentz force is completely obtained from the Lagrangian. Through, directly you can obtain the Euler-Lagrange equation from the Lagrangian, but in this class we obtained the Hamilton's equation to reproduce the Lorentz force. But this one can also be applied to the fully relativistic case, and the addition of the electromagnetic potential is this, minus potential is this. And this one is the free particle Lagrangian for the massive particle. And if I combine these two things and follow the exactly same style of calculation, we can find the conjugate momentum. Again, conjugate momentum is expressed in this, so the replacement should be made in comparison with the free particle case. What we have to do is just to replace the momentum with the P minus Q over CA. And tedious calculation will give, but you can also replace PC with PC minus QA, just like what you have stated before. Finally, our force is expressed in the momentum's time derivative, but this is not a conjugate momentum, but mv gamma, right? So please distinguish with this small p that is expressed in terms of velocity. This is capital P is the dressed one, which has the vector field. Finally, our final result for the Hamilton's equation for the relativistically moving charged particle is again Lorentz force. So Lorentz force is a completely relativistic expression. That's it.